All right, everybody. I wanted to start off this first video. I'm going to go ahead and recap the entirety of the Organic Chemistry 1 course. And so what I want to do is I want to make videos for the entire course going back from day one and reviewing all the rest of the material that we have yet to put on video, that we have yet to do for the rest of the semester. And so this will be good for you guys if you want to review a particular concept or maybe even in future semesters. And so I thought a good place to start off would be to go back to Lewis structures and review what a Lewis structure is, because ultimately to talk about organic chemistry, you're really going to need a really good understanding of Lewis structures. And so what I want to do is start off with those things, Lewis structures. And I'm not going to go through a step-by-step explanation of how to draw Lewis structures, but what I do want to do is make sure that everybody's familiar with how do I draw a Lewis structure, what kind of geometries Lewis structures represent, and how to count electron groups, how to count bonds, and how to count for formal charges, because those are important concepts that you have to be able to do just to start organic chemistry. And so let's start off with something as simple as methane, CH4. Now, when I think about the Lewis structure for CH4, I'm going to add up all the valence electrons for all of the different atoms, and I'm going to get 8. And if you don't know how to add up valence electrons, then we'll take a look at that in another video. But at the end of the day, we're going to look at the periodic table. So I'm going to do is I'm going to draw a single bond between all the atoms and check for octets. I've used up all the electrons. I've got an octet around everything. And again, an octet is really a word that implies there's something about 8. And really we mean 8 electrons. But at the end of the day, octet's just a formalization that we're going to use to say, does the atom correctly have enough electrons in order to be in its lowest energy configuration? And at the end of the day, most atoms are going to want 4 bonds or 8 electrons or some combination between bonds and electrons to add up to 8. But other atoms, an octet means something else. And of course, the first exception to that is hydrogen. Right? Hydrogen only wants 1 bond, so that means it's only looking to have 2 electrons around it. So an octet for hydrogen is really just 1 bond or 2 electrons. Boron is another example of an exception. Boron is in group 13, and group 13 elements, specifically boron and aluminum, if you're thinking about drawing them in a covalent bonding sense, they're only going to want 6 electrons or 3 bonds. So an octet for boron is 3 bonds. And so at that point, really what an octet is, it starts to become flexible. Even at the heart of the word, it means 8. And so anyway, we're back to drawing Lewis structures. So here's an example of CH4. We've drawn the Lewis structure with the valence electrons that are available to us. Everything has an octet. So we just assume we're done with the Lewis structure. Now that may be true, and we may be done, we may not be done. And there's other things that we're going to have to check later on, and we'll talk about that in a little while. The first thing that I want to talk about right now is what's the geometry? And what I mean by the geometry is 2 different things. I mean the electron geometry, and I mean the molecular geometry. And these 2 things are slightly different. The electron geometry is what we refer to as the parent electron group. It's the geometry of the molecule, including bonds and lone pairs. And this is coming from Vesper. Valence, oops, let me redo that. Valence shell electron pair repulsion theory. Vesper, that's what Vesper theory is. And so the basic idea behind Vesper is that electrons don't want to be next to each other, so they push themselves as far away as possible. And we'll use BH3 as an example to kind of talk about that as well. But right now, back to CH4, we want to figure out what the electron geometry is. And the way that we do that, the easiest way is to count electron groups. An electron group can be any bond. That means any type of bond. So later on, we're going to talk about double bonds and triple bonds. But when we're counting for electron geometry, we count any type of bond only 1 time. So if I had a double bond, I would only count it once. Now it's going to be counted differently later for formal charges, And so we'll think about that here in a second. So when I think about the electron geometry for CH4, I think about counting the number of electron groups. And at this point, remember, an electron group is any bond or any lone pair. In this case, I have 4 bonds to hydrogen and there are no lone pairs. So the electron group, when the electron geometry, when there's 4 electron groups, is tetrahedral. Now, the next thing that I want to consider is the molecular geometry. The molecular geometry considers only the atoms. If there were a lone pair, we want to talk about the geometry that only the atoms make. Now let's get back to tetrahedral for a second. Why is tetrahedral the geometry based on the fact that electrons don't want to be next to each other? If I think about it, a tetrahedron provides the longest possible bonding, or the largest possible bond angles between each of these atoms. And so what I've drawn is drawn a representation of the bonds. The wedges, and this is going to be true for all of organic chemistry, wedges mean that they come towards you. Dashes mean that they go away from you. So if I were to draw these hydrogens in perspective, this hydrogen would be a little bigger than both of the other ones, and this hydrogen would be a little smaller because it's in the back. And so it's really important to be able to see molecule shapes in 3 dimensions. And if you can't do that based on a drawing, I know that my drawing's not the greatest, but if you have a difficulty doing that based on pictures on a page, then my suggestion is to get a model kit. I know they're 15 bucks, they're 10 bucks or something like that, but the investment in that model kit is essential if you are not one of those people that can just see in 3 dimensions. It doesn't have anything to do with whether or not you're smart. It really is this interesting separate type of skill is 3-dimensional visualization. And so this is a 3-dimensional depiction of what a tetrahedral molecule is. So the molecule is tetrahedral in its electron geometry, and the molecular geometry considers only the atoms. And so since there are no lone pairs, the molecular geometry is tetrahedral as well. And so what I want to get to right now is some of the things that we can glean from the fact that we've decided that the electron geometry is tetrahedral. All of the facts about the molecule as far as bond angles and eventually hybridization, we can get that from the electron geometry. When we think about an electron geometry that's tetrahedral, this leads us to 109.5 degree bond angles in an ideal situation. And so what we mean by that is that the bond angle here is 109.5 degrees. And this would be true between any of the bonds in the tetrahedron. Okay, so that's CH4. And for right now, I want to leave it right there with bond angles. We've talked about the geometry, both the electron geometry and the molecular geometry, and the bond angle that we can get from that. Later, what we're going to talk about is the hybridization, the number of sigma bonds, and the number of pi bonds. But before we do that, we want to talk about molecular orbital theory and valence bond theory. So we're not quite there yet. So let's go through the basics of Lewis structures first. Now let's take a look at BH3. And so I want to erase it over here, and I'll redraw it down here. If I think about the number of valence electrons that I get to draw a Lewis structure from BH3, it's going to be 6. I've used 6 to draw the picture, and I'm left with 0 electrons. So we're going to say boron has an octet. An octet for boron is 3 bonds or 6 electrons, so we're okay with this. So what's the electron geometry here? Well, since there's 3 things, the furthest away that 3 groups can be is actually in a plane, and the bond angles in this case would be 120 degrees. Since it's in a plane and essentially it's in the shape of a triangle, it's called trigonal planar. All right, and so what's the molecular geometry? Well, the molecular geometry is the same, again, because there are no lone pairs. Remember that the molecular geometry describes the shape of the molecule, but only considering the atoms. All right, so this is a couple of basic situations, CH4 and BH3, when you have things that don't have lone pairs. But let's take a look at what happens when we do have lone pairs. And a couple of immediate examples of that will be ammonia, and let's see, ammonia is a good example. And let's see, water is another good example. Both of these things have lone pairs. And so when we think about the electron geometry for ammonia and drawing the Lewis structure, remember, we're going to put the central atom, usually listed first, in the middle. We're going to put the other atoms in between around, and I typically draw them as symmetrically as possible. And now I'm going to count electrons. Now, again, from the periodic table of electrons, I got 5 for nitrogen. I got 1 each for hydrogen, so that gives me a total of 3. I'm back to 8. And so what I want to do is I start off by drawing a single bond between every atom. I think about how many electrons I used in drawing those 3 bonds. I figure out it's 6 because it's 2 for each bond. That leaves me with 2 electrons left over. Well, that's good. It's okay that I have 2 electrons left over because nitrogen doesn't have an octet, which, remember, in this case, it means some combination of bonds and electrons that, for nitrogen, gets us to 8. Now, remember, again, for hydrogen, it only wants 2, and so the hydrogens already have octets. And so once I've added that lone pair, I've used all my electrons, everything has an octet, so I say, okay, I'm done. So what about the molecular geometry, or the electron geometry in this case? Remember, the electron geometry is determined based on electron groups. I count electron groups by counting lone pairs or any type of bond. Well, what kind of lone pairs and bonds do I have? I have 3 bonds to hydrogen, so that's 1, 2, 3. And I have a single set of lone pairs, so that's an extra 1, so 3 and 1 is 4. So I have I have 4 electron groups, and 4 electron groups means I'm back to this tetrahedral electron geometry. But I want you to notice, does this look like a tetrahedron? No, the answer is it really doesn't look like a tetrahedron. And that's because when we draw pictures of Lewis structures, they're not really related to the actual geometry of the molecule. They're just ways for us to keep track of the electrons and the predicted bonding in the molecule. And from that, we can say what the predicted geometry should be. When we draw the Lewis structure and we see 4 electron groups, no matter how we end up drawing it, we say to ourselves, this is still a tetrahedral electron geometry. So if I were to draw it in 3 dimensions to show the electron geometry, I would use one of the parts of the tetrahedron to take into account the lone pair. I still have a bond coming towards me and a bond coming away from me. And let me clean it up just a little bit. There I'm back to that tetrahedral shape. So that's the electron geometry. Again, it's the geometry of everything, including lone pairs of electrons. But what's the molecular geometry? Well, the molecular geometry is the shape of only the atoms. So what if I take away the part of the molecule that includes the lone pairs of electrons? This is what I should describe as the shape of the molecular geometry. And in this case, it's maybe a little bit difficult to see, but it's essentially a 3-sided pyramid. And what do I call a 3-sided pyramid? Well, I got a word for it: trigonal pyramidal. So I've come up with this idea that the electron geometry is tetrahedral because, remember, back in the day, there was 4 electron groups, but the molecular geometry is the geometry of only the atoms, and the atoms make the shape trigonal pyramidal. And so one last thing I want to think about are, what are the bond angles? Well, remember, bond angles are based on the electron geometry, and at the end of the day, it's still ideally 109.5 degrees. But at the end of the day, there is some repulsion provided from the lone pair, and so it actually pushes the bonds away from it a little bit. And so what we say is that it's something less than 109.5 degrees. So it's not quite 109.5, maybe it's 108, maybe it's 107.62, whatever. It's not 109.5, it's a little bit less, but at the end of the day, you're not wrong if you say 109.5 degrees. What we wanted you to get at is that the ideal bond angle in anything that has an electron geometry that's tetrahedral is 109.5. In a real life situation, if it's got a lone pair, it's going to be a little bit less than that. But I would suggest that on most exams and quizzes, you're going to see it say 109.5. All right. So what about water? What about H2O? Well, if I think about the number of electrons that I get from water, I'll end up with 6 from the oxygen and 2 from the hydrogen. So that gets me 8. I'm going to arrange the atoms just like I did before with the central atom in the middle. The central atom typically is listed first, but in the case of water, hydrogen is listed first. And one thing we know is that hydrogen is never the central atom. Now that I've drawn one bond between each atom, I can take away those electrons, and I've drawn 2 bonds, so that's 4 electrons. I've got 4 electrons left. Well, oxygen still needs an octet, so I'll use those other electrons to make lone pairs to describe that water is got an octet. So I still have a combination between bonds and lone pairs of 8 electrons. Okay, so let's think about this. What's the electron geometry? Well, again, we got 1, 2, 3, 4 geometry groups. When we think about counting the geometry groups, it's any pair of electrons, that's 1. The other pair of electrons, that's 2. And then any type of bond. The single bonds only count once, just like doubles and triple bonds. So that's 4 total electron groups. So what electron geometry does that lead to? That leads to a tetrahedral electron geometry. Again, if I were to think about what the shape of the molecule is in real life, I've got 2 lone pairs on this picture that is a tetrahedron. So I'm still putting it on the basic shape of a tetrahedron, but I'm using lone pairs in 2 locations now instead of 1 location as I did with ammonia. So now that I've figured out the electron geometry, I can go ahead and say, look, what about the bond angles? Well, the bond angles are going to be the same as they were before because they're based on the electron geometry, and it's 109.5 degrees because that's the bond angle that goes with tetrahedral geometry. Now again, it's going to be less than 109.5 degrees because the lone pairs are going to repel the actual bonds and push them away a little bit further than the ideal bond angle. But the number that we're looking for to make sure that you understand what electron geometry we're talking about is 109.5 degrees. All right, so what about the molecular geometry? Remember that the molecular geometry is the geometry of only the atoms. So let me take away these lone pair of electrons and let's think about what this shape is. Well, chemists are not particularly inventive in the naming of different geometries, and so we've got these two bonds. They're not directly apart from each other. They're kind of at an angle, so we'll just call it bent. This is a bent geometry, and that's the name of it. So it's got an electron geometry of tetrahedral because it had 4 electron groups, the 2 lone pairs and the 2 bonds, but it has an actual molecular geometry of bent because when I take away what the 2 lone pairs, the 2 bonds that are left are not directly apart from each other. They're at an angle, so I'm going to call it bent. All right, and so that's a couple of different ones. That's tetrahedral. That takes care of tetrahedral pretty well. But let's take a look at some other situations. What if I had CO2 or maybe N2? Let's think about those molecules and how we deal with that. All right, what about CO2? If I think about CO2, I'm going to get 4 electrons from the carbon. I'm going to get 6 from each of the oxygens. So that's a total of 6 plus 6, that's 12 plus 4. If I did my math right, I think I should have what? 16, if I did my math right. So let's put that number down just in case. So now I'm going to draw a picture of the molecule, and I'm going to put that central atom in the middle. The first atom listed, of course, is the central atom in this case. And so I'm all right. I've got carbon in the middle and the 2 oxygens on the end. All right, so now what am I going to do? I'm going to use my lone pairs and this are my electrons, and this is important because you have to do it in this order until you're really good at figuring out where the bonds are and what's a double bond and what's a triple bond. What you have to do is you have to just say to yourself, I draw 1 bond between each atom first, and I remove those bonds from my count. So I'm left with 12 electrons, and the next thing I should do is make an attempt to get octets around everything by making lone pairs. This is a systematic way of doing Lewis structures. And so if I think about it, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got octets around the oxygens, but I've only got, I don't have an octet around the carbon. And so in order to make an octet, what I have to do is once I've used all of the electrons and I still don't have octets, that's the signal to me that I use multiple bonds. Again, first, you have to draw the 1 single bond between each atom. Then you have to attempt to make lone pairs count up all the octets. In other words, let me say that a different way. Use lone pairs to make octets. If you run out of electrons from your valence electron count, that's the clue to you that you need to make lone pairs into multiple bonds until you do have octets. So if you notice, I have all of the lone pairs, all of the electrons already on the page. And so what I want to do is I want to erase some of the lone pairs and use it to make a double bond. And so do you see what happened there when I took one of the lone pairs off of oxygen and made a multiple bond with it? Oxygen still has an octet. It still has 8 electrons. Carbon now has 1 extra pair of electrons, so it went from having 4 to having 6. It doesn't quite have its octet, so what I'm going to do is I'm going to grab a couple of electrons from the other oxygen, draw a double bond on this side, and now carbon has a full octet. So I'm good to go on carbon. I'm good to go on both of the oxygens. I've used all of the electrons, so I'm done. What about the electron geometry here in this case? Well, I want to count electron groups again. Now, remember, before I was counting 4 and 3 electron groups, but now how many electron groups do I have around carbon? I hope you're saying right now 2, because remember, a double bond, a single bond, and a triple bond all count the same when I'm counting electron groups. Later, we're going to count valence electrons for formal charges. That's not the same method that we use. But right now, for electron geometries, any kind of bond counts exactly the same. And so I have 2 electron groups. What geometry is the result of 2 electron groups? Linear. And so now I know that it's a linear geometry. The molecular geometry is still the geometry considering only the atoms, but in this case, I don't have any lone pairs on the carbon, so it's still linear. Well, what are the bond angles associated with this? Well, if you remember geometry from 8th grade, in order to have a line, the angle must be 180 degrees. And so that's what the bond angle is. It's 180 degrees. All right, now for our last example. We're going to do nitrogen, or N2. So N2 is a diatomic molecule. Each nitrogen brings in 5 atoms for a total of 10 valence electrons. So what I'm going to try to do is draw that single bond and reduce the electron count by what I did. Remember, I'm going to do this first, then attempt to make lone pairs, 1, 2, 3, 4, 5, 6. Now that's got an octet. And then use 7, 8 to try to get octets. Remember, this is the clue that tells me I'm ready to make multiple bonds. And so I continue to make multiple bonds until I have octets. But what I have to do is I have to erase electrons, because remember, when I used those lone pairs, all the electrons or the valence electrons in the molecule are already on the piece of paper or on the page. So I'm going to use one of those lone pairs to try a double bond to see if that works. Well, the nitrogen on the left still has an octet, but the nitrogen on the right is still missing a pair. It's only got 6. So I'm going to keep going, right? Because I can make double bonds and I can make triple bonds. So I'm going to erase yet another lone pair and use it to make a triple bond. And so now let's just double check. I started with 10. I've got 1, 2 on the, I've got 1, 2 on the right, 3, 4 on the left, 5, 6, 7, 8, 9, 10. I've got all of my electrons. I've used them all. Everything has an octet, so I'm done with this. Well, what's the electron geometry? We don't have a handy dandy rule for this, because which one is the central atom? I guess it doesn't matter. You can pick one that's central atom and you can say how many electron groups are there. Well, in either case, you would pick either nitrogen. And in either nitrogen, you would say it only has 2 electron groups. One is a lone pair and one is the triple bond. Remember, the triple bond only counts once. And so the electron geometry is still linear. Now, of course, you could have said to yourself this, because if you remember geometry from 8th grade, the only possible geometry between 2 points is a line. And even if that thing that connects those 2 points is a triple bond. So that means, of course, then the molecular geometry is also linear. All right, here's a trick question though. What's the bond angle? What's the trick question? There is no bond angle. Why isn't there a bond angle? Because you got to have 3 atoms to get a bond angle. In order to have an angle, you must have 1, 2, 3 points. And so clearly the geometry is linear, but the bond angle doesn't really make any sense because we don't have more than 2 atoms. And so that's it for the review for Lewis structures. This is how you'll do Lewis structures for the rest of the time in organic chemistry. Remember, from a general chemistry, there are other more complicated Lewis structures, trigonal bipyramidal and octahedral, and all of the molecular geometries that are associated with those electron geometries. But by and large, in organic chemistry, we don't really consider those particular geometries because we're going to be dealing with carbon, nitrogen, and oxygen for the most part, and those things can't do expanded octets, and they don't make trigonal bipyramidal or octahedral electron geometries. So at the end of the day, that's all we want to do for this particular video. I'm going to leave it right there. And so if you have any questions about Lewis structure, send me an email, put it in chat, put it in the comments, whatever you want to do, and we'll see if I can't answer it in a short video or send in an email or something like that. Thanks for watching, guys.